All right, welcome to the third video where I'm taking on the hardest parts of the paper 1 questions. In the meantime, I've realized that I did some adding integers wrongly because the total marks in the first video was not 37, it amounts to 42 marks. Still a grade 3 though, and same goes for the second video. I found 1 mark too much there. It should be 41 marks. So if you do everything in the first 2 videos together, you have something like 83 marks, which still would be a, a convincing 7 on the mock test that we did before the summer break. But at the real exam, you should think of it as being a safe and comfortable grade 5. In this video, we attack the 2 remaining questions, which is number 8 and number 12, and they are only 26 marks. But as I said in the last video, in the actual exam, you should sort of expect there to be more of the difficult questions and slightly less of the easy and medium questions. So if you're aiming for a grade 6 or 7, then you should at least be able to do some of these really hard ones. You'll also notice that these questions, they are the reason that I usually say you have 1 minute per mark, but as you can see, it's a 2-hour exam and there is only 110 marks in total. So if you do the calculation there are sort of like 10 minutes left. And these 10 minutes, you really need them for the hard parts in this video, because you will notice that you will sometimes have to spend some time really just staring into the ceiling, trying to get the right idea and how to make things connect. But with all that said, I'll just get started. So, question 8. 9 marks, so you have around 9 minutes plus a few extra thinking minutes. And what makes this question really difficult is that it looks harmless. Well, it's just trigonometry, you say. But then it's so not transparent what they actually want you to do. So it is also very confusing. And it turns out to be very little trigonometry and actually quite a lot of vector calculus instead. But it starts out with a parallelogram, meaning that the opposite sides are parallel and equally long. And we are being told that the vector going from the point O to point A has a name. We call it A. And this is going very slowly. No, that's all right. And the vector from O to C is called C. It's down here. And of course, that means that the vector over here from C to B is also A. And the vector from A to B is equal to the vector from O to C, in case we ever wanted that. Well, actually, we're going to want that. So the vector going from A all the way to B, that is actually our vector C as well. The angle between the vector A and the vector C is called theta. It's the guy down here. And then we have this point M. Well, we're also being told that actually the length of C is twice as much as the length of A, and that will come in useful later. And you can kind of see how this starts getting confusing with a lot of information. So how do you actually draw that? You don't. You just try and remember for later. And then we're being told that M lies somewhere on the line between A and B, and that the distance, or the vector from A to M, is some number k times the vector from A to B, which we remember to just be the vector C. So in fact, the vector going from A to M, it's a bit hard to draw here on top, is actually k times C. For that part that goes to M. And Furthermore, the dot product between the vector A and the vector from the vector from O to M and the vector from M to C is equal to 0, which means that the angle between them is a right angle, which they also have been so kind to put in the drawing, that it's the angle up there is actually a right angle. Then question A, then we can start working, says that we have to express OM, so the vector from O to M, and MC in terms of the vectors A and C. And if you look at the drawing, then OM, this guy, is actually equal to the vector A, that's really nice, plus the vector from A to M, which is K times C. And I can sort of understand how this is easily confusing, because they say that we have to express the vector in terms of A and C, but this is expressed in terms of both A and C and this number K that we don't know. So that's also a thing that you have to get used to, that you kind of have to stop all the confusion by thinking, well, there's no way of improving this because we do not know the value of K and we have no idea what the vector from A to M is, and that is the vector that we need to add to A. So there is absolutely no way of simplifying this or turning this into something that has nothing to do with K. Because if K changes the value, then the position of M changes, and then the vector from O to M is a different one. So of course it's going to rely on what the value of K is. So that is what they actually mean by expressing in terms of A and C. There is no other way of doing it. Similarly, we also want to express MC. And again, if you look at the drawing, then the vector going from M to B, so MC we can make by taking the vector from M to B and adding the vector from B to C. And nice enough, the vector from B to C is just the opposite vector of vector A, so that's just subtracting A. We have to be a bit careful not looking too much at the drawing, because the vector from M to B is not C. C is going all the way from A to B, but the vector from M to B is what we get if we take the entire vector from A to B and we subtract the vector from A to M. So what we do is we take C minus KC, and that's the vector from M to B, and then we subtract vector A. So another way of saying that is just saying 1 minus K multiplied with vector C, and then subtract vector A. And again, there's no way around using K as well to express this, but these are the results for A. So in B, I'll gladly admit that I took quite a while to realize what they mean by use. So the word hence is very important. It means that now you have to use what we just did. And then they say use a vector method to show that something is equal to 0. And this something is very non-transparent. But the idea here is to sort of remember that, is there any calculation that I know is going to be equal to 0? And that's where at some point maybe the dot product is the way to go. And you might have to try 3 different things and realize that it's never going to look like the equation they want. But if you keep asking yourself, what is the calculation that I know is going to be 0? Then you might look around and see that, well, this is equal to 0. And that also fits with the word hence, because we just found a way of expressing exactly OM and MC. So this sort of gets us started, that the equation that we certainly can write down is that the dot product between OM, which is A plus KC, dot product with 1 minus K times C minus A. And that's definitely 0. So how do we clean up this mess? Well, the dot product behaves like any other product, that if you have a dot product between a sum or difference between vectors, you can sort of just make the dot product on all terms. So we get 4 terms here, and when we have a scalar, this 1 minus k, that's just a scalar, similarly the k here, then making a dot product with a vector and then a vector that has had a scalar multiple on it, you can just save this scalar for afterwards. So you can sort of do the dot product of the vectors first. So that means that if you take 1 minus k times the dot product of a and c, that's from the first 2 terms, and then you subtract, because there's a minus on this a here, k times the dot product of c and a, which I'm going to write because the dot product is commutative. So that's just one more of these guys. And then the cross terms, then we get minus the dot product of a with itself, that's the norm of a, squared. And finally, the product between the other cross terms, we get a plus. And then we get k multiplied with 1 minus k multiplied with the length of c squared. And that's still equal to 0. And you might say we are still so far from having the equation we want, but it's going to clear up soon. Because first of all, the first 2 terms, they are very, very similar. And in fact, they can just grow together because we have, well, you could even say that the first term is 2 terms in itself. It's 1 times the dot product of a and c, and then minus k times the product of a and c, and then another minus k times the dot product of a and c. So these guys we can actually turn into 1 minus 2k times the dot product of a and c, which is really nice, because if you look at what we are aiming for, then 1 minus 2k has to be a factor in all of it. So that's pretty nice that this shows up. Now, the dot product of a and c, we actually want to also think about that, because as you can see up here, we want the angle, actually the cosine of the angle theta, to turn up. And remembering that theta is the angle between a and c, then we need to remember something else. Namely that the dot product of 2 vectors is the same as the length of the 2 vectors multiplied, and multiplied with the cosine of the angle between them. So the dot product can actually be turned into the length of a times the length of c times the cosine of theta. And that starts looking pretty nice. Then, of course, we still have minus the norm of a squared, and we have plus this awful k times 1 minus k times the norm of c squared. And this is still 0. So far, so good. Now we want to remember that the length of c is actually 2 times the length of a. And this is useful because, as we can see, the expression we want, this thing here, has nothing to do with the length of c. So we want to get rid of the length of c. So instead of having the length of c, we're going to write the length of a multiplied with 2 everywhere. So what do we get? We get that 1 minus 2k times the length of a times the length of a again. So that's the length of a squared, but we get a 2 because the length of c is twice the length of a, times the cosine of theta. And that looks really nice because, as you can see up here, this is actually the part we get when we multiply a norm of a squared times the bracket into this first term here. So now we just need to get the last bits. In the last bits, we also take the norm of c squared, and turn into the norm of 2 times the norm of a squared. So that's so this guy here is going to be 4 times the norm of a squared, because the 2 also gets squared. So the last two terms, they're going to have a squared as a common factor, and I can already anticipate that I want to subtract, because up here I have a minus. So I'm actually going to put a minus, and then I'm going to take the norm of a squared outside a bracket, and then the first term is just a 1, and then comes a minus, because this is a plus, and the minus is going to be a plus, and then I'm going to move the a squared outside, so what remains is 4 times k times 1 minus k, and this is 0. And as you can see, this is starting to look almost right. At least we have the norm of a squared that we can have on both terms, so we can put it outside everything. And then we also need 1 minus 2k. This is definitely a factor on the first term, but we also need that as a factor on the second term. So our tribulations are not over, because what we have here is pretty nasty. It is 1 minus 4k plus 4k squared. And where should we even write this? So I'm actually going to take one more line. So what do we have? We have 1 minus 2k times 2 times cosine of theta, which is perfectly fine, and I'm not going to do much more about all that. And then we get minus this weird bracket. And I'm just going to change that now. I'm going to turn it into what I just said, 1 minus 4k plus 4k squared equals 0. Now, what do we do from here? So in this expression here, we think it would be so nice if this was actually equal to this 1 minus 2k multiplied with the 1 minus 2k that is in there. And if you think about that for just 2 more seconds, then you realize that, hey, when I do that, when this 1 minus 2k is multiplied with this, then I get 1 times 1, which is 1, and then I get the second term squared, this 2k squared, that's 2k times 2k, that's the full k squared. And then I get the double product, like I get the 2 times 1 times 2k, which is 4k, subtracted because of the minus in there, and that's exactly this guy. So what we realize is that this shit is actually 1 minus 2k squared. And hooray, that means that the 1 minus 2k is a factor that can go outside the bracket again, and then we get, let's just write it down here, even though you don't have that option. We get the norm of a squared, and we get the 1 minus 2k outside the bracket, and inside the bracket for the first term is only 2 times cosine theta left. And for the second term is just minus one of these factors, 1 minus 2k. And this is equal to 0. And hooray, we are actually there. But wait a minute. This was only the first 5 marks in this question. So what's left is question C, and we have no more space. So let's just simulate that this is an exam. So question C, I'm going to say see my answer booklet, and then I'll continue there. Oh, I found my answer booklet, and of course I'm going to write my name very carefully. I think I had 1 page left in the answer booklet from the last video, but there is no limit to how many answer booklets you're allowed to order, and it's a really good idea to just get an answer booklet for every single question you're going to fill out. So in this answer booklet, I'm going to very carefully write that this is about question 8. And you could even write something here like continued, because we still have a question left. And to answer question C, they tell us to now find the range of values of theta such that there are 2 possible positions for m. And how do we do that? Well, the 2 possible positions sounds a lot like 2 solutions for an equation. And so that if that equation happens to be a quadratic equation, it sounds a whole lot like a discriminant being positive. That's the first clue in all of this. Then second, you kind of need to think, where do we come from? And you can see that on the left, that we have found out that regardless of what the values of theta and k are, then they must fulfill the equation that we just found. So very carefully at that equation, and I can't really point at it because I'm working on the answer booklet, but the underlined equation that we found in question B. And you think that, okay, we are given the vector a already, so the norm of a squared is just a number that we already have. What's in question is what can the values of theta be in order for there to be 2 possible positions of m. And the position of m is really what k is about, because for every value of k, we get a different position of m, and k has to be between 0 and 1. So you kind of realize that the equation there is an equation about k. For a given value of theta, this is an equation about k, and if you look really carefully at it, you realize that it is actually a quadratic equation, which is really nice. So if you look at it like that, then it would be nice to have it in a sort of standard form. So we take the equation that we found, and I'm going to take it again. Say it's the norm of a squared multiplied with 1 minus 2k multiplied with 2 cosine of theta minus 1 minus 2k. And all that is 0. So of course we can start by just dividing with the norm of a squared on both sides. That'll just make that go away. And then I just realized that I was about to do something really stupid, because I was about to just multiply everything out here to get a very nasty equation that I wanted to say that the discriminant has to be positive. But first of all, that's going to be a mess to write up. And second, the discriminant being positive is not quite enough, because that'll ensure that we get 2 solutions, but not that both solutions are between 0 and 1 as they have to be. So in fact, it's a good idea to stop yourself here and just realize that, hey, it's actually much nicer to have the equation in a factorized form, because you can already say that this equation always, regardless of the value of cosine of theta, always it has a solution when this first bracket is equal to 0, and that is when k equals 1/2 is always a solution. Which kind of makes sense if you look at the drawing, that regardless of what angle you make between A and C, as long as C is twice as long as A, then the parallelogram you make, you can always put M right in the middle of A and B, and you will get a right angle. If you do a little bit of trigonometry on that, it actually makes sense. So the question is really that the other part, 2 times cosine of theta minus 1 minus 2k, this thing must have a solution that is different from 1/2. So must have a solution k that is between 0 and 1, and also where k is different from 1/2. So if we just start trying to solve it, then we get that we can sort of open the bracket and put everything on the other side. We get that 2k equals 1 minus 2 times cosine of theta, or k equals 1/2 minus cosine of theta. And you can sort of say that this means that this solution is actually an interesting solution if cosine of theta cannot be 0, but it can be anything up to, but cosine of theta can be anything above 0 and up until it's equal to 1/2. When it becomes equal to 1/2, then the other solution is 0, and that doesn't make sense. So that is the range of cosine of theta. It's allowed to be, so cosine of theta is allowed to be in the interval from 0 to 1/2. And then to get the value of theta, you also need to memorize that there is the unit circle where cosine is equal to 1/2 when the angle is the one we used to call 60 degrees, but now it's called, let's see, both. This is something I always struggle with. That's pi over 3. And that means that theta is allowed to be in the interval between, so this is when cosine becomes 1/2, and then it's allowed to go until cosine becomes 0. So it's from pi over 3 to the right angle, which is pi over 4. But wait a minute. In fact, theta could also be bigger than pi over 4, because then k would just become a negative value, but the solution we found up here. So we kind of just need to realize that this solution up here is also fine when it's negative. When cosine of theta is negative, then we're just adding a negative number. So cosine of theta can also be anything that is larger than minus 1/2, except for 0. So we kind of have the possibility of cosine of theta being between 0 and 1/2, or between minus 1/2 and 0. So we kind of also get these angles where this angle is 2 pi over 3. So we just need to change our mind regarding this, saying that we are allowed to go all the way to 2 pi over 3, but we're not allowed, we can write that like this, but we're not allowed to take theta as pi over 4, but because in that case cosine would be 0, and then k would be 1/2, and it would be the same solution as the one we started out with. So there would not be two possible positions. So this is the answer. And as you can see, that took a fair bit more than just 9 minutes, which explains why it's a good idea to put 1 minute per mark, even though the truth is that you have a little bit more. Oh, and another thing, I said twice that a right angle is equal to pi over 4, which is also totally not true. The right angle is called pi over 2. And now I'm dead serious that this is the answer. Moving on to question 12, a 17 marks section B question. So I go to my formula booklet and I write carefully on the top box that now we're answering question 12. This is another binomial expansion, and we just can't wait to get our hands into question A, where it says that we have to actually do the binomial expansion of the expression cosine theta plus I sine of theta. That looks a whole lot like a mixture between complex numbers and binomial expansion. And this is what makes the hard questions hard. It's that you have to think of two very different topics at the same time, raised to the power 5. But for question A, we almost need to not think about complex numbers at all, because we just do a binomial expansion as we always do. So we can just write, it is the sum where r goes from 0 to 5, and each time we take the binomial coefficient, that is 5 choose r, times the first term, cosine theta, raised to the power, let's say 5 minus r, you can also say r if you prefer, times I times sine of theta raised to the power r. But we actually need to write this out in a form where you can see what part is a real number and what part is an imaginary number. And there's allowed to be sines and cosines of theta in both parts. So we are actually supposed to write every term of this 6-term sum. And we just start. So the first one is when r is 0, 5 choose 0 is just 1. And then we get times cosine of theta to the 5. And the other guy gets raised to the power 0, so that one disappears. The next term gets a plus, and then we have the binomial coefficient 5 choose 1, which is 5, times cosine of theta raised to the power, that is now 4, times I times sine of theta to the power 1. So I don't really need a power for that. So far, so good. Then we get plus the binomial coefficient 5 choose 2. And 5 choose 2, you might want to do it with like 5 times 4 divided with 2. But spoiler, it's going to be 10. And then we have cosine of theta to the 3rd power, and this time we get I times sine of theta to the 2nd power. But I'm already going to say that the I squared is just going to make this a minus, and then we get sine of theta squared. The next term is 5 choose 3, which is the same as 5 choose 2, because the binomial coefficients are symmetric. So from now on, we are not going to get no new binomial coefficients. So the next one is a 10 times cosine of theta to the power 2. And you know what? I'm also going to turn this up here into a 10 right away, because it's nicer, times, and now we get I raised to the power 3. So the I to the 2 becomes a minus out here, and then there's one I left, times sine of theta to the 3rd, and then we get plus 5, that's the binomial coefficient 5 choose 4, times cosine of theta to the power of 1, times, and this time it's I times sine of theta to the 4, so the I to the 4 is just 1. So it's minus 1 squared, it's 1. So this is just sine of theta to the 4. And finally, the last term is plus binomial coefficient 5 choose 5 is 1, times cosine of theta to the power 0 disappears, and then we could just get I to the power 5, which is I times sine of theta to the 5. And this is almost it. We just need to make sure that we get the real part separated for itself. That is this term, and this term, and this term, and the imaginary part for itself. So writing it up again, it is cosine of theta to the 5 minus 10 cosine of theta to the 3rd sine of theta squared, and finally plus 5 cosine of theta sine of theta to the 4. And that's the real part. And then we get plus I multiplied with 5 cosine of theta to the 4 times sine of theta. And then we get minus, from the middle term, 10 cosine of theta squared sine of theta to the 3rd, and finally plus sine of theta to the 5. That's the imaginary part. And the first line up here is the A, and the bracket after the I is the B. That's for question A. Then comes question B and says, now use De Moivre's theorem to and your answer to part A and show that sine of 5 theta equals something. So De Moivre really just says that this cosine theta plus I sine of theta, that's what we also call the cis of theta. If you raise that to the 5, you just get cis. So let's write it out. That cis of theta to the 5 is really just the same as cis of 5 theta, which is cosine of 5 theta plus I times sine of 5 theta. And this is the exact same thing as the thing we had above. So what we see here is that they want us to find an expression for sine of 5 theta, which is the imaginary part of this guy, which is what we call B, which is in the bracket up here. So we can really just say now that sine of 5 theta is equal to the stuff that we put in the bracket, that is 5 times cosine of theta to the 4 times sine of theta minus 10 cosine of theta squared sine of theta cubed plus sine of theta to the power 5. And what do you know? That is not what they wanted us to get. So we have a correct expression for sine of 5 theta right there. And if we look at what they have, we sort of see what's the problem. The problem is that they don't want cosines. They only want sines. So what's the next step? It is to realize that cosine of theta is equal to the square root of 1 minus sine of theta squared. Or actually, this is true for certain values of cosine, but I actually prefer saying that cosine squared of theta equals 1 minus sine squared of theta, because all the cosines I have is cosine to the power of 4 and cosine to the power of 2, which is really nice. So we can rewrite this as 5 times, so instead of cosine theta to the 4, I say 1 minus sine of theta squared squared. That's cosine of theta squared to the power 4 times sine of theta. And then I get minus 10 times 1 minus sine of theta squared times sine of theta cubed, and finally plus a single sine of theta to the 5. And this starts looking really nice, because what do I get when I start multiplying things in? I am going to copy this. So if you had a paper version, it would be very easy for you to just look on both pages at the same time. But I don't have that luxury. Instead, I can do this sort of magic and say, this guy, I can turn that into 5 times. So what do we get from this quadratic thing, like 2 terms to the power of 2? I get 1 minus the double product 2 sine of theta squared plus sine of theta to the 4. And this is multiplied with sine of theta minus 10 times, and I'm going to put this sine of theta cubed into the bracket. So this is sine of theta cubed multiplied on the 1 minus sine of theta to the 5. That's what you get with sine of theta squared is multiplied with sine of theta cubed. And finally, a sine of theta to the 5. And if you count all these up, then you get 5 sine of theta to the 5. And you get plus 10 sine of theta to the 5. And you get a single one extra. That's 16 sine of theta to the 5. And then what else do you get? You get sine of theta cubed. You get minus 10 of those. And then minus another 10 here. That's minus 20 sine of theta cubed. Sine of theta cubed. And finally, you get plus 5 sine of theta, which I hope is exactly what they wanted us to get. So, hooray! That's question B. So, racing on to question C. Okay, sorry I got interrupted yesterday and I have to continue the day after. This is why I suddenly wear a different color t-shirt. We are at question C of this last problem 12. And for this, it becomes surprisingly nice. We're being asked to show that these two angles, theta equals pi over 5 and 3 pi over 5, are solutions of this horrible equation that, yeah. And the nice thing is that the equation, the left-hand side, is very similar to the stuff that we have just worked with, showing that it's equal to sine of 5 theta. If we look carefully at it, the coefficients are exactly the same, but the powers of sine aren't quite right. So if we realize that the sine of 5 theta that we just worked with is actually equal to this 16 times sine of theta to the 4 minus 20 sine of theta squared plus 5 if all of this is multiplied with another sine of theta. And we are being asked to show that these two numbers are solutions to the equation where this is equal to 0. And it's very easy to get confused, because if you read this as we have to show that these two numbers are the solutions, then we might actually think that we have to find every single solution to this equation. And that's very difficult because there are infinitely many. Just the sine of theta at the end, if this is 0, and it is for infinitely many values of theta, then we get a solution already there, which is not the ones that they suggest. So a priori, this equation has infinitely many solutions. But we're just being asked to show that these two particular numbers, so for theta equals, for instance, pi over 5, then we have to realize that if we take sine of 5 theta, we just get sine of pi, which is 0. And similarly, for theta equals 3 pi over 5, if we take sine of 5 theta, then we just get sine of 3 pi, which is also 0. So that means that if we plug these two values of theta into this whole thing, then we get 0. But that might actually be because sine of theta is 0 and not because this factor is 0. So we also need to check that if we actually take sine of theta itself, we get either sine of pi over 5, which is definitely not 0, and similarly, we get sine of 3 pi over 5, which is also definitely not 0. It doesn't really matter what they are, just that they are not 0, so it means that, therefore, it must be the bracket here that is 0 because of the null factor law. So if a product is 0, then it's because one of the factors is 0, and we just checked that sine of theta is not 0 for these two, so it must be this guy. Therefore, the two values must be such that 16 sine of theta to the 4 minus 20 sine of theta squared plus 5 must be 0 for these values. I just realized that I forgot to fill out this very important box up here saying that we are still working on question 12. But that was just part 1. There is a part 2 that says that hence we have to show that this weird calculation, sine of pi over 5 times sine of 3 pi over 5 is the square root of 5 over 4. And this is also one of these head scratchers where you kind of have to think, what does that have to do with what we just did? So the trick here is to realize that, let's just go on another page and say this is still question 12, but now it's CII. The trick is to realize that if we look at the equation 16 times x squared minus 20 times x plus 5 equals 0, then what we have realized is that if we plug in for, so this one has roots. What we just found out is that if you take sine of theta squared and put into this when theta equals either pi over 5 or theta equals 3 pi over 5, because then we get exactly the stuff that we showed in 1 when we take theta to be one of these two values and we take sine of theta squared and we put in here when we square the value of, so this is x, when we square that, then we get sine of theta to the 4, and we just take it here, we get sine of theta squared. So that's exactly what we showed in part 1, that this becomes equal to 0. So that means that for these two values, and sine of theta squared is a root in this quadratic equation. And then we need to switch to a completely different topic again, because now we need to think about roots in polynomials. And one thing that comes to mind is that if you take the product of the roots, then you get actually the constant coefficient divided with the coefficient of x squared. So that means that if you take sine of pi over 5 squared and you multiply with sine of 3 pi over 5 squared, the point is that you get 5 divided by 16, because that is the product of the roots in a quadratic polynomial. And from there, we are pretty close, because we just need to take a square root on both sides. So both sides are positive. So if we take, so sine of pi over 5 and sine of 3 pi over 5, they're both positive because the angles, they're smaller than pi. So we can rather confidently say this means that sine of pi over 5 times sine of 3 pi over 5 is actually the positive square root of 5 over 16, which is the square root of 5 divided by 4. And we should say, since both sine values are positive. If we didn't say this thing, then we might doubt that it could have been equal to the negative square root, but it's not. And that's what they asked us to get. And what do you know? We actually survived the last question. But as you can see, question 12 is for the people who are very, very bored with the questions in the first two videos, because this is not easy. Anyway, I hope you enjoyed this walkthrough and that you will be back for 3 more chapters of paper 2. See you then.